So this is a video review of metabolism, energy transfer, and an introduction to enzymes. So our first question is, what is metabolism? And we just define metabolism as all the chemical reactions that are going on within your body. Okay, so maybe you hear of some people that have a high metabolism, some people have a low metabolism. Really, that's dealing with all the chemical reactions and the energy transfer within their body. So we have a little equation here, and I already had you watch the video on Gibbs free energy, and Mr. Anderson I think does a good job of explaining, but just to give you some definitions here, we do not need to do really any calculations for this. You just need to understand the relationships here, and I'll get more into detail there when I get on to the next two questions. But you will be given the equation, so you don't have to memorize the equation, but you need to know what they stand for. So Gibbs free energy is going to be the delta G, or change in G. Another way to say that is going to be the available energy. So what is actually available in this system? Delta H is going to be the change in enthalpy, which is the total energy in the system. And delta S, or the change in S, is going to be the change in entropy, or the randomness. Okay, molecules are spread out, or are they together? So again, taking a look at the video, I think Mr. Anderson does a good job of talking about what entropy is and enthalpy is, kind of getting the difference there. And then finally, T is going to be our temperature, and that temperature is going to be in Kelvin. So what we just want to understand is the relationship between these variables, and we're going to take a look at a couple reactions here. And the first one is going to be cellular respiration. So first we're going to take a look at the variables and what happens, and why G, the available energy, is going to be less than 0. So during cellular respiration, we have a change in the amount of total energy. So that is actually going to decrease. Okay, and I'll show you the graph for that on the next page. Now, in the process of cellular respiration, one of the byproducts is going to be heat. So we're going to raise our temperature. And then we are also going to have a change in the entropy, or the randomness of the molecules. And again, I'll reference this in the graphs on the next page, but again, Mr. Anderson kind of talked about this as, what happens to sugar? It breaks apart and it becomes more random, and the energy is going to be released. So that's why G is going to be less than 0. The other reaction is going to be photosynthesis. So photosynthesis is going to have a G value that's greater than 0. So let's take a look at what happens. We're going to take sunlight to run this reaction. So that sunlight is going to store energy in the bonds of sugar. So our actual total energy is going to increase in the system. There is no change in the temperature because photosynthesis doesn't absorb, doesn't release heat, okay? But there is going to be a decrease in the entropy, or the randomness of the molecules. So you're going to take water and carbon dioxide, and those molecules are going to be kind of floating around, right? That's going to be high entropy, and then it's going to combine to form sugar, and so what's going to happen is the entropy is going to decrease, or the randomness. Okay. Again, pause if you need to, go back, kind of listen to the relationships here, what's happening. So if you solve for these, if I decrease the H but I increase the T, and I increase the S, and I'm going to subtract, well, that means G is going to have to be really small. If I increase the H and I decrease the S, that means my G is going to be larger. So if we take a look at a graphical representation of this, we can also identify these as exergonic, or exothermic reactions, and then endergonic, or endothermic reactions. So you remember exer, exit, leaving, exo, leaving. So this is energy that's being released in the system. We talk about an exothermic reaction is going to release heat, whereas ender and endo, taking in or absorbing. Okay, so the exergonic is going to release energy into the system, G is going to be less than 0, and our example is cellular respiration. Endergonic or endothermic reactions require energy input, and they're going to store energy in the system, so our G is going to be greater than 0. And our example is going to be photosynthesis. So here is the graphical representation of what I covered on the last page, and this is kind of what I want you to see. Let's take the energy first. Here is the energy of the reactants, and here's the energy of the products. Well, what's happened to that total energy? The total energy has decreased. Okay? So remember on the previous page, that's going to be our delta H. Delta H has decreased during cellular respiration. Okay? What's happened to the entropy? Entropy, so we've got this sugar molecule, they're all bonded together, C6H12O6, and it's a nice, neat little package. But then when you undergo cellular respiration, what are you going to do with that? Well, you're going to break it up into water and carbon dioxide. So there's going to be more entropy. There's going to be more randomness in the system. So again, what's happening to our randomness? What's happening to our entropy? The delta S is going to go up. Okay? And then I also said as energy is released, some of that energy is going to be released as heat. Right? So that means my temperature is going to go up. Okay? And so here's a classic example of an exergonic reaction, which is going to be cellular respiration. On the other side, we have photosynthesis. Okay? In our system, let's take the energy first of all. Here's our energy of our reactants, and here's our energy of our products. What's happening to the energy total in that total system if this is going to be our energy? Energy is increasing. So, again, going back to our previous page, delta H, energy in the system is increasing. Okay? So we're going to use sunlight, and we're going to run this reaction, and you're going to take those molecules of water and carbon dioxide and combine them into sugar. So what's happening to the entropy, what's happening to the randomness of those molecules is it's actually going to decrease. Okay? And so 2 ways to represent it. You can use a graph, or you can use Gibbs free energy to understand those relationships. And that's what you need to be able to do. Okay? Now, this is a unit on energy transfer, so we should talk a little bit about the main energy source for living things. And that's going to be ATP. ATP stands for adenosine triphosphate. And we should kind of recognize the molecules that make it up. You know, adenine, right? If you remember, double ring, okay, so that's going to be found in nucleic acid also, so that's a nitrogenous base. Here's a ribose, that's going to be a sugar, and then we've got 3 phosphate groups. Okay, so this is kind of showing the atoms that are going to be present. Here's more of a larger scale molecular model of that, showing the adenosine or adenine, and then the ribose, and then the phosphates there. Okay, now really it says 2 high energy bonds, but really when we use ATP, we're going to use only that last high energy bond. We're going to break that one, and that's what's going to give us the energy for cellular processes. Okay, and so here is our example, again showing the elements present. When we take ATP and we break the bonds, or break the bond here, that is going to release energy. It'll release about 7.3 kilocalories for every mole of ATP, okay, and that's used for the cellular processes. So when you break that bond, that's going to release energy that can be used in the system, okay? Now the beautiful thing about ATP is it can be reused or recycled, I should say. So when you release that phosphate, you're going to have ADP, adenosine diphosphate. So you're now only going to have 2 phosphates. But what you have the ability to do is take a little energy and recombine the ADP plus the P, and you can go back to ATP. Okay? So we can say ATP can be reformed by combining the ADP and the P. When a P or a phosphate is added, we say it is phosphorylated. So we're going to see that term used quite a bit. Phosphorylation, it simply means that you're just going to add a phosphate. Okay. And we'll get into more details. You might think, well, you know, if I break a bond, I get energy, but then it's going to take energy to recombine that. We'll talk about when we get to cellular respiration. It doesn't take as much energy to make the ATP as the energy that's released from it, okay? So there is a benefit to being able to do that. All right, so another topic that we have is going to be enzymes. So why do we talk about enzymes with this? Well, if we want to run in those chemical reactions like cellular respiration and photosynthesis, it's going to require enzymes. And we do this right after we talk about biochemistry because enzymes are going to be proteins. So they are going to have a specific shape to them. They are catalysts. And catalyst means that it's going to speed up chemical reactions. So without our enzymes, the chemical reactions in our body wouldn't take place. And some of them wouldn't take place at all. Some of them would be so slow that it wouldn't allow the reactions to happen at any type of feasible rate, okay? So how do they speed up chemical reactions? They speed up chemical reactions by lowering what we call the activation energy. So I'm going to use the graph here. The activation energy is kind of like the hill, all right? So think about this. I got to roll a ball. I got to roll a ball up to the top of the hill. Once it gets to the top of the hill, what is that ball going to do? It's going to roll down, okay? But it takes some energy to put into the system to push that ball up to the top in order for the reaction to run. So what enzymes do is they actually make that hill shorter. So this purple line is a reaction that does not use an enzyme, so it takes more activation energy, and then the reaction will occur and we'll have the products. Well, if you use the dotted line, you're going to use an enzyme. So hill is shorter, doesn't take as much energy, and the reaction still takes place. Okay, notice the products are going to be the same here, but it's this hill here that's going to be different. Okay, how do enzymes lower activation energy? Well, they're going to have a specific position on the substrate. Substrate is what they're going to work on. Okay, so whatever that enzyme has to fit with, it has to position itself correctly. It strains the substrate bonds. So if we want to take a compound and break it apart, it's going to strain the bonds and allow that reaction to happen faster. And it can covalently bond to the substrate. So when it combines, binding to that substrate is actually going to lower the activation energy. All right, last thing. In some enzymes, they need a cofactor or a coenzyme. So we talked about the fact that we're going to have a specific shape for proteins. So here's my enzyme. It's not active though. It doesn't have the right shape for my substrate. So I'm going to have a cofactor, coenzyme, that has to fit in first. And then when that fits in, then the substrate will actually fit. So in some cases, not all enzymes, but in some cases, the enzymes, if they're going to position the substrate correctly, they are going to have a cofactor or coenzyme. Okay? Vitamin B12 is a great example of something that's going to be a coenzyme, cofactor, that's going to allow you to have cellular respiration occur at a faster rate, release more energy. So that is a review of energy transfer and an introduction to enzymes.